So we have converted a differential equation. So you can think of finding the unknown solution as finding it on all the infinite points between 0 and 1. Yeah. So if I knew the solution, this function u at every point between 0 and 1, that's like an infinite number of points. It's an uncountably infinite number of points. And that's what knowing the solution essentially means. We write it down as some expression and so on. But yeah, there are an infinite degrees of freedom in a smooth problem. And we have converted it into a linear system with finite number of unknowns. Okay, so this is like a standard thing in scientific computing or numerical analysis. You replace a more difficult problem by a simpler problem with infinite degrees of freedom by finite number of degrees of freedom. You might replace complicated functions by polynomial approximations. You might replace integrals by evaluations of functions in the so-called numerical quadrature, and so on and so forth. Any reasonable textbook on numerical analysis will start out by saying all these nice things about numerical analysis to sell the field. Okay, so we have done that, and like I think perhaps it was Vignesh who was asking the question, if I read that right from the participants list. So yes, I have swept the thing. There is some more things to be shown, but I've assumed that this linear system is solvable. It's this matrix is non-singular. Okay, and therefore there is a unique solution. You need to show this a little. This is usually a thing you have to show. It's not a difficult proof, but we'll leave it out. Okay. So then if I solve this, I have the unknown solution at all the grid points, and that gives me my, so I can then just linearly interpolate between those two grid points, and I have a piecewise linear interpolation of these solution points. That'll give me a numerical solution to the Poisson's equation. Okay. Okay, so then the question is, how do you even solve this linear system numerically? How does one quote unquote invert the matrix, so to speak? Okay, and for that there are very many methods and procedures and things to consider depending on how the matrix is structured, whether it's a sparse matrix. Does the matrix have like a billion unknowns, or is it only like 10,000 unknowns, and so on and so forth? And here is a one slide overview of solving such linear systems. Okay. In a basic course on linear algebra, you might have studied about row echelon form, or computing the Jordan form of a matrix, and sort of solving linear systems in that setup. But that's just basic linear algebra for the sake of introduction. Okay. In practice, one uses something like a LU decomposition or Cholesky's method if the matrix is symmetric and positive definite. For like reasonably small sized matrices, you can easily solve 1,000 by 1,000 or even a 10,000 by 10,000 matrix on your computer in under a second if with these kinds of methods. Okay, and these are for so-called dense problems. Okay, so I think I already made a reference to it once in this. Oftentimes it's computation is not, the cost is not computational cost, but these days it's more and more memory costs. Okay, so if I had a billion by billion matrix, I can't even represent it, even if I had like probably, I mean, I can do some rough calculation, but unless I have like 100 GB of RAM or memory, I wouldn't probably be able to even represent all the entries of a billion by billion matrix. And it might even not make sense because lots of these entries might be zero if it's coming from some physical process for reasons, again, beyond this discussion. But perhaps very gently, I can say, like, the Laplacian discretization itself is local. So you got that banded structure because of that local discretization, and that will follow through. So you'll have like a banded matrix if I took a billion points between 0 and 1, and most of the points of the matrix would be, entries of the matrix would be 0. Okay. So for such cases, you might try and use things like iterative solvers. Some of these are more friendly for parallelization. The Jacobi's method is embarrassingly parallel, and you could use this for some medium-sized matrices. You can't, although I mean, I said you could use it for a billion by billion. In practice, you don't, because there are so many other considerations in linear systems from a numerical perspective that are not sort of at first sight even visible when you just look at it as a linear system problem. Okay, there might be things with condition numbers, where are the eigenvalues of this matrix spread. I mean, then there would be floating point errors to contend with in the algorithm that you're using. There are many, many things. Okay, so more typically, people would use something called as Krylov subspace methods, and you might have heard of conjugate gradient in an optimization context, maybe. I don't know. So this is like the most popular amongst these methods. It works for symmetric matrices. Our Laplacian discretization turns out to be a symmetric matrix, so you could throw in conjugate gradient to solve that problem. And then there are, for non-symmetric versions, there are this generalized minimum residual or GMRes. Then there's MinRes. There's like a family of such methods. And then like the cutting edge, again, just a little plug for people to know about linear system solutions. Even like people do research, cutting edge research in something like solving AX equal to B. And the cutting edge methods that I know of are so-called geometric and algebraic multigrid methods. And I mean, if you're like pursuing research into your future, or you want to pursue things in the industry, whatever you do, and you want to use linear system solutions, if you have not heard of it before, you might want to consider algebraic or geometric multigrids. Okay, these are so-called agnostic to the underlying geometry of the problem, and try to think of the matrix as some graph and do some fancy things. Okay. And with all of these, you could do some kind of preconditioning. It'll be inevitable. There's this idea called preconditioning, and studying all of these usually is a course in and in itself. Okay, so if you're thinking of going to grad school, you might consider taking a course on just studying linear systems in addition to things like whatever else that you're generally interested in. Okay, so
any papers on that, geometric and algebraic?
Oh, there is for geometric multigrid, there is a popular book. I mean, no papers. Some of these have books. Algebraic multigrid might still be in the realm of papers, but geometric has been around for a while. William L. Briggs, I think, Briggs, that's the author's name. William L. Briggs, I think. It's called a multigrid tutorial. That's where you start if you want to learn geometric multigrid. Okay. And if you Google algebraic multigrid, you'll find Wikipedia entries probably, and you can always look up, or you can mail me later, and happy to share more. Okay. For all of this, again, a good reference is something called a SAD, Yusuf Saad, SAAD, large parallel linear iterative linear systems, or something like that is the name of the book. Saad was in fact the person who introduced GMRes in like the 1980s, I think. So yeah. Okay, so this is a plug, because we will be solving linear systems. You should know at least the theory where it's coming from. I mean, even though we can't study each of these methods, you should know when you do a MATLAB / or you do some sort of a solve in one of these scientific Python stacks, you should know what's going on a little bit, if not the algorithm itself, that something like this is actually going on under the hood. Okay, so we are sort of done with the Poisson in 1D. We can now move on to the Poisson in 2D. Okay. Again, maybe I'll wait to see if there are lingering questions. You want me to revisit any slides before we move on? We are kind of at halfway, I think. Okay, so let's do this then. So our model problem is now going to be the unit square, just for fun. We could have taken a disk also, but easier to deal with unit square. And again, we'll only consider zero valued Dirichlet boundary conditions to keep the discussions reasonably simple. Okay. So that's my Poisson problem. I've explicitly thrown in the x and y's to show that it's a two-dimensional problem. So u is a function of xy. My right-hand side is a function of xy. That's my same Poisson problem. Given u of xy is now 0 on this. I mean, it's this is the unit square. Omega is this whole two-dimensional square. And the boundary of the square, which is that line bounding it, on that u is 0. Okay. So here is a analytical solution, a simple one. If I picked f is pi square sine pi x sine pi y, I can check that it first of all, I can totally I can integrate this. It's kind of variable separable and so on. I can integrate it and check that this is indeed the solution. Alternatively, you can do, like it is like NP hard versus NP complete, whatever. As a loose analogy to it, if I told you this is the solution, I can totally take the derivative twice and get this right hand side and check that the solution also satisfies these boundary conditions. Yeah, so I can do that check more easily than if integrating out. But even for integration, this problem is not so difficult. It's straightforward. It's the same problem again. For even a reasonably complicated f, this approach is going to not yield us anything. Okay. And the other thing which I have not mentioned, but is always there, is that domains are not such nice intervals. I mean, forget 1D. Nobody is going to do any 1D problem. Even in 2D, you're not going to have nice domains like zero square or disk or whatever. You're going to have complicated domains. And even if your right-hand side function is nice, the domain might sort of screw your life up. You can't write down the integral and so on with a complicated domain. So again, we have to retort to numerical solution. And we have already sort of studied or talked about it. The only devil is in the details, which is bookkeeping the variables and so on. So the principles are sort of all the same. It's just tiny bit of bookkeeping that we have to deal with. Okay. So here is the Laplacian in 2D, partial square u by partial x square plus partial square u by partial y square. And here is the discretization that we wrote down for the 1D, written for the 2D. And our grid is going to look something like this. Okay, so we'll again keep life simple by saying delta x equals delta y, although you can make it, not only can you make delta x and delta y not same, from between point to point, you might even like make delta x and delta y different. Okay, so that's like the most general thing, but that's not illuminating in a first cut. So we'll keep everything simple. Here is a nice uniform grid. And yeah, so you have to bookkeep. So you have to say this is u of 0, 0, because its I is 0, j index is 0. This is u of 1, 0, and so on. Like this is u of ij, I plus 1j, I minus 1j, and so on. There's a time variable as well. Ignore that for the moment. Okay. For this problem, there's no time, so you can ignore the superscripts. Okay, so the matrix for this is going to be a bit more complicated. So, I mean, this is not exactly for this problem. If I write it down, this will have like 36 by 36. Instead, I'm showing it for a 9 by 9 problem. Okay, and this is how the matrix is going to look like. Instead of 2 minus 1 and so on, we'll get 4 minus 1 and so on. Okay, it's called as the stencil. So this is the stencil, minus 1 minus 1, 4 minus 1 minus 1. And this has some structure. Okay, that's why these lines and vertical and horizontal lines are drawn. This has like, this is a block matrix of 4 minus 1. It's the Toeplitz block with 4 minus 1. And this is the identity block, and this is the 0 block. You can check that this is what these blocks are. Okay, so there's something called as a Toeplitz matrix. I would ask you to look it up, but if you don't know what that is, it's not going to make a difference. So we have some linear system which we have been able to assemble into like this matrix, and we just solve this linear system. Use any one of those solvers that we discussed before. Okay, so here comes the first problem with this finite difference approach. Okay, So that's the end of my discussion on finite difference. I'm going to conclude it with these problems and therefore do a different discretization, which will in the final setup yield the so-called famous Cotan formula that we'll get to. Okay, so I could have put some more take a stock of where we are kind of slides, but okay, I missed it, and maybe in a next iteration I'll do it. Okay, so here is where we are. We have looked at the finite difference method and it seems okay. Nothing seems to be wrong with it, but there is a problem. I mean, there's always a problem. Okay. The problem is that the structured grid in the discretization, something like this that I have like this lattice of points in 2D. In 3D, it'll be like a cube, it'll be, the lattice will be sort of extending in the third direction as well. Okay. So the lattice of points means if there is some graphical model I'm dealing with, I mean, maybe it's the famous dragon or even the Stanford bunny. There might be some small features in it that I can't allow my discretization to overlook. So my discretization grid, this lattice, is going to be dictated, its size is going to be dictated by the smallest features in my problem, which means that if the features are kind of varying in scale, I'll have like a unnecessarily super big grid, like where in most of the regions I wouldn't need such a big grid, but the smallest features in my problem will dictate that I would need to have this unnecessarily superfluous grid everywhere. Okay, which in turn has its repercussions for solving the linear system itself. It might just be untenable. I mean, people might laugh you out of the room if you say that I have to use a supercomputer to run my gaming engine. Yeah, so this can have problems. So I mean this idea is very uh, simple and sort of promising or very charming to look at. And this is what people did in the 70s and 80s when computational thing was like, you could do only small problems, 1,000 by 1,000 systems. People were happy doing things like this. But we have moved on. So I already sort of referenced that large systems, there's some art to it. Okay, so the problem is you can't use this finite difference method for anything really practicable. Okay, although we'll use it to show some illustrations today. Again, this is a learning course. We're not trying to do cutting edge research in this course. So we'll use it, we'll understand it, and then when we actually go down to working on real meaningful problems, we'll use more sophisticated methods. Okay. So I kind of want to also point out that lattice grids cannot be used if there are curved boundaries. I mean, how would you have a grid that is also curved on the boundary? People have dealt with it. I mean, there are these conformal mappings and so on. People have come across this problem before, have dealt with it, but these are not clean solutions or solutions you want to keep even today. Those were solutions in the past when there were other motivating reasons for pursuing them. But today we can do better things. Okay. So that's that point about if you had curved boundaries, you'll have to then embed the object in a bigger box, which you will then discretize and so on and so forth, which will introduce unnecessarily some extra variables which were not even part of the original problem. So we will seek alternatives if they exist. And it turns out there is a standard alternative, which we can next talk about. This alternative is called as the finite element method. Okay. So the finite difference method was one method for solving a Poisson's equation, or more generally PDEs. It can be spatial derivative, like PDEs with spatial and temporal variables. The idea is kind of generalized in a meaningful or a reasonable manner. And now we are dealing with a second method for solving a Poisson problem in 1D, which is called as the finite element method. So here is how it goes, and I'm going to be a little more sparse on the complete details. Okay, so I'm not going to tell you what precisely these terms mean, but what we do in the finite element method roughly is the following. Earlier, we started by discretizing this like this second derivative, replaced it with difference quotients. Now we are going to discretize that solution space that I sort of alluded to earlier. Okay. And to do that, I'm going to convert this. This is called as the strong form, original form of the PDE. I'm going to write it down in so-called weak formulation, which means instead of asking for the equality of the PDE, I'm going to ask for some integrated quantities to be equal. Okay, so I integrate both sides. I first multiply both sides by some arbitrary v of x coming from some function space that is yet undefined. Okay, here it is already defined. It's the function space of all L2 functions on 0, 1. So what I've done is I've taken u double dash x equals f of x, minus sign is always there. I have written it down as u double dash x times v of x equals f of x v of x. If v is not 0, this equation makes sense. And then I'm integrating it from 0 to 1. That's what I've done. Okay, this is called as the weak formulation. Okay, instead of like integrate saying it's equal in an integrated sense, you might even say it's equal in the inner product sense. What you have done is an inner product, but okay, let's not go there. Then what I do is that there is a very versatile tool in basic calculus called integration by paths, and I'm going to do that here. So instead of, I take this left hand side integral and I use integration by paths, and I move one of the derivatives over into the other function. So sometimes, or in this setting, this function v is called as a test function, but it's okay if you don't know that. So so I moved the integral over to this other function v, and I end up with a boundary term. So if you remember integration by paths, you replace one integral by another, and then there's some boundary term. Okay, so that's what I get. The boundary here is for the boundary of the integral, okay, which corresponds also to the boundary of the domain. And there is a typo everywhere. This should be 0. This should be 0. Okay, it's showed up some places. Okay, so this left-hand side I modify, I do integration by paths. And now I have a boundary condition which says that u is 0 at x equal to 0, u is 1 at x at 0 at x equal to 1. And this boundary term involves u prime v of x. So what I'm going to do is, initially I said I'll just multiply this by some arbitrary v of x. But now I'm going to pick the v of x such that v is 0 at x equal to 0 and 0 at x equal to 1, which means this function v mimics the boundary behavior of the unknown solution that we are seeking. Okay, what this buys me is that this boundary term then goes to 0, because u prime, I don't know, it might be some values, but I know that v of 1 and v of 0s are zeros, so I can sort of, it'll be like this, one of the terms in the product is 0, so this drops out. Okay, so then I have this problem. So I have, using integration by paths and this weak formulation and integration by paths, I've converted this PDE into this problem here. Okay. And now I have to say something about the function v of x. One thing that I already said is it has to be mimicking the boundary conditions for the given problem. The second thing is that it has to be in L2 at least, just like my u. And u is actually in L2, its derivative is in L2, its second derivative is in L2. But now I'm taking a derivative of v as well, so I want its derivative to be also in L2. Okay, think this L2 is important because of physical motivations like energy not blowing up and so on and so forth. Okay, now we come to the finite in the finite element method. So I have these functions. This is so-called function space. These contain functions which are in L2 and derivative is in L2. And I pick a subspace which is called as a finite dimensional subspace. So linear algebra is, at least in the beginning, is like study of finite dimensional subspaces. Infinite dimensional subspaces do pop up in linear algebra itself, but more honestly, they are studied in something called as functional analysis. And spaces of functions is an example of infinite dimensional space. Okay, so what we are doing is we are just taking some finite subspace. Okay, very loose analogy is like if I have the line R, I'm just taking an interval of R and calling it a representative of R. Okay, that's a very loose analogy that you can help think that's what I'm doing when I'm picking this finite dimensional subspace of V. Okay. And here is the technical condition, which I'm not going to totally talk about, but I think I have a figure that illustrates it. Because this space is finite dimensional, it has a finite basis. Okay, and I'm going to pick a finite basis, which is also compactly supported. We have already encountered the term compactly supported in this discussion. So that's something we know. It's going to have a basis of functions which are going to be zero outside a small finite region. Okay. And then this finite element method in the, so that's the element. The elements are basis functions which are compactly supported, and the method comes from so-called Galerkin's method, which says that I have set up this finite dimensional subspace. I started with this L2 functions whose derivative is in L2, whose functions are of this same boundary condition as my given data. And I've taken this finite dimensional subspace. Galerkin's method simply says that I have to find my U also in this subspace. This is what I meant when I said you approximate the solution space in the finite element method. So I've picked up I'm not seeking U anymore in this L2 intersection C2, which was discussed earlier, but instead I'm going to seek it in this finite dimensional subspace. Okay. So here is a rephrasing of all of this again with some more illustration. Okay, so here is so I've started with my Poisson problem, written down my weak formulation. I've said I'll pick this finite dimensional subspace, and let me explain or give you an illustration of what it is on 0, 1. Okay, just like before, I'm going to subdivide 0, 1 into intervals, and I'm now going to pick basis functions which are compact like the following. So here is an illustration. You can leave this out for the moment, and there are many basis functions here. So there are the blue dots like before is the discretization of 0, 1. So this contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. Okay, there are 11 points. There are 10 elements if you want, so regions between the points. If I picked this point, this is the basis function for this point. This, I hope the colors are coming through, and I hope nobody is colorblind, but this purple color curve that I've shown here, that's the basis function associated with this point. Okay, and it's 0 everywhere else. It starts from 0 here and becomes 1 at this point, and again falls back to 0. It linearly does all this. Okay. This function is useful to be aware of, to know, to learn, because again of its multiple uses in graphics. Okay, so this is called as the hat function. There are 11 points. There are 11 hat functions. Each hat function has this property that if it's the ith hat function on xj data point, grid point, it'll be 1 only if I equals j, otherwise it's 0. So it looks like a tent if you want, and that's why it's called a tent function as well. Some people call it a hat function because it looks like a hat. But it's aside from this discussion, it's related to something called as barycentric functions, which are sort of important in graphics processing on their own. Okay, so this is something for you to write up or make a note of if you want to get to reading it again in future. These functions pop up not just in numerical solution of partial differential equations, but within graphics itself for graphics processing tasks and things like that. Okay, so what I'm doing now is I'm using these basis functions and which each of them is a nice linear function. I can write down this linear equation. If I take this green function, I can write down its expression for this line. I can write down the expression for this green line. Everything else is 0. So it's a linear function. Its derivative is a constant. This is positive constant, negative constant for this green function. I can compute each of this easily now. And I can compute this integral, therefore. I mean, it's just a product of two constant functions which I integrate constant numbers or constant values. I integrate it from 0 to 1. Okay. So these uj and vi are not part of this integral. They are some constant values themselves. So they'll come out. And with a little bit of algebra, you can show that it leads to a linear system of this form, ku equal to b, where this matrix k, I should have used a, my bad, but there's a reason I used k. In the finite element community, this is standard notation is k, but it's okay. So in linear systems community, the standard notation is a. You'll have to deal with these kinds of little nonsense issues. Okay, so this is called as the stiffness matrix. It comes from essentially this derivative product integral. Okay, so and this right hand side b is this. Now I mean in the finite difference method, I just took this function and evaluated it at the grid points. Now I have to do something more. Okay, I have to take this function and integrate it against these functions, and this integral can be same way. It can be complicated because my f could be a complicated function, even though this basis function is simple linear function. This integral may not be computable, and then I'll have to resort to so-called numerical integral rules or methods. But I can do one approximation. I can quote unquote project, I can represent. I mean, you might, if you have a signal processing background, you might have said like, average value of a signal, then in a Fourier series, you'll try to write it down in terms of its harmonics and so on and so forth. So I can sort of try and write this function f in this basis. That's an approximation that I can make. So I should have said approximately equal to here, but that's okay. So I can write down this function in terms of these basis functions, which fortunately is easy. So what you do is just take the value of f at each of the nodal points, and that just gives you the value corresponding, a coefficient corresponding to this basis function. This is called within certain like subfields, it's called Lagrange interpolation of a given function. So these are also called as Lagrange polynomials, these linear basis functions. And so what we are doing is a Lagrange polynomial approximation of f of x. And there are some fancy computationally cheap ways of doing it using, again, this idea called as barycentric functions that I referenced. Okay, there's something called as barycentric interpolation that will give me this almost like in constant time. Okay, in the size of the input interval. Okay, so then now I once I've done this approximation, these two are now easy enough functions. These are just two linear functions. I can compute its integral in even a closed form integral of it. So if I don't do this, I call my right hand side. If I don't do this approximation, I call my right hand side b. If I do this approximation, I can pull out this fk as a vector f, and I have this integral of these basis functions. This integral assembled into a matrix is called as a mass matrix. Okay, it would have been helpful if I had written that down. So this M is called the mass matrix, K is called as the stiffness matrix. And if you, I believe you were exposed to a little bit of libIGL. If you go to libIGL, you would find this, at least you'll find mass matrices. There's like a couple of these mass matrices in libIGL, which is like a Voronoi mass matrix, a barycentric mass matrix, and a mass matrix which they have not implemented, which precisely corresponds to this problem. Okay, and then the stiffness matrix also you will find in a package like libIGL. It's called as the Cotan matrix, which we will get to a little bit later towards the end of this session. Okay.